We've been talking about this AdaBoost. In general, we're talking about the boosting approach or the boosting. Let me start in a fresh board. We're talking about the boosting paradigm. And the boosting paradigm in general is that you want to learn some class. So we want to learn some class H, and we do it so we pick a class B for basic classifiers. With the goal that usually so that ERM over B is easy, so that empirical risk minimization over B can be carried out fast. Usually this means efficiently. And then we pick some a boosting rule. And a boosting rule is a rule that tells us how to go from a hypothesis HT in this class and a sample. So this is an update rule given a labeled sample S, a distribution dt over S, and some HT in B. It determines how to pick dt plus 1, ht plus 1, and some weight wt plus 1. So we have this kind of boosting rule. And now what we do is, given a sample, given a labeled sample, training sample, S, we start with let D0 be the uniform. So say X, S is X1, Y1 up to Xm, Ym. And D is the uniform distribution over X1 to Xm. Right, and now we pick HT. We pick at each stage step T. We pick HT that belongs to the ERM with respect to the sample S and the distribution dt. So we give each point in the sample some weight, and making an error on this point counts according to this weight. And we want to minimize the total ERM over B. So we want to minimize the weighted error of a hypothesis. Does it Are there any questions up to here? We've done it all last time, but if there's anything unclear, yes?
What's the significance of t plus 1? Like, what are these steps t?
OK, so let me just finish the description. So we pick this hypothesis ht. We have a distribution dt, which gives you kind of a way to weigh the elements of S. Which one is more important? Then it defines this notion of ERM with respect to this distribution. It tells you an error of every point counts as much as the distribution gives weight to this point. And you want to minimize the total weight of the errors. Right? And we assume that we use our efficient algorithm to find H in the set B that minimizes this weighted error. And now we have some rule that define us, apply our rule, apply the update rule to determine the t plus 1, and then you continue. And the update rule will be of the form that for every point on which the ht made an error, dt plus 1 will give this point more weight than dt gave it. And every point on which ht did not make an error, dt plus 1 will decrease the weight of this point. Yes? What is what? OK, WT, I haven't got to it yet. But so the update rule is the following. You have some distribution over the set of points. And this distribution just tells you how much you weigh each arrow. So the weighted arrow, the arrow of, with respect to dt of some h, is just the sum over I goes from 1 to m of d of xi times 1 according to whether h of xi is different than yi. So this is the characteristic function. It is 0 if this condition is not met. So if we don't make an error, it's a 0. If we make an error, it's a 1. So if we make an error, we are paying the weight of the point xi. If my function h makes an error on xi, I compare it to the yi in my training. If my function h makes an error on xi, then I'm paying the weight of the, xi. So this is what is the error with respect to a probability d of h. And we want to minimize the error with respect to dt. Each time we have a different dt. Yes?
Because what you said last time, I think, was that this error is effectively for d plus 1 and the other one. And so this is how you're finding the error for dt plus 1 from dt, right?
No.
Or that's the error.
That's the error that I'm minimizing here. When I said empirical risk minimization,
okay.
The thing that I want to minimize is the error of ht with respect to dt.
This dt, okay. So, yeah.
So I want to find the ht that will minimize this error with respect to dt. I'm giving these weights to the points, and I want to find a function in my class that minimizes the weights, the total weights of the error that the function makes. Yes?
How did you say the weights are updated for
I didn't say how the weights are updated. What I'm saying is that what I call is a boosting paradigm is a rule that tells you how to update the weights. It's the rule that tells you how to update the weight. And we had some formula on how to update the weights. And the only general thing about this rule of how to update the weights is that we want to increase the weight of points where we made an error and decrease the weights of points where we didn't make an error, where we were correct. So we apply the update rule. So this update rule depends on your specific algorithm. In the AdaBoost algorithm, it was a rule which was some kind of an exponent of your error. So we have an update rule that tells us how to transform the distribution dt to the distribution dt plus 1. Now that I have a distribution dt plus 1, I will take ht plus 1 to minimize the error over s according to dt plus 1. And I'll keep moving. So each time I have a hypothesis, I have a weighting function over the points, and I can calculate the weighted error. Yes?
What is the original distribution?
The original distribution, I mean, we have a training sample that came from some distribution. Now we forget about this distribution, we are working with the sample. It's a rule of how to work with your sample. So you start, d0 is the uniform distribution over the points of the sample. So each of them gets weight 1 over m. Then we find the error minimizer. Since B is a restricted class, it is not likely that we'll find something with 0 error. So every h in B will make some errors. So now we update the distribution. It was initially uniform, but now we give more weights to the points on which my first h erred and less to those on which I was correct. And I keep going. And finally, so what happens here is that we are just chewing over and over on the sample S. It is just internal computation on the sample S. We take the sample S, we find the error minimizer, we define dt plus 1, and run it over again. So the output of this process is a sequence of functions, h1, h2, ht, and so on. Now we decide on some stopping criteria. When will we stop? We could either decide in advance we are going to stop after 100 steps, or we are going to stop after the algorithm ran for 2 seconds, or we can decide we are going to stop once my empirical error becomes small enough, or once the empirical error doesn't shrink anymore, looks like it stabilizes. So I have some stopping rule, and I end up with some ht. And now the output of this algorithm, now I need to output a classifier. The output of the classifier is the sine of the sum of wt ht, and that's where, from 1 to t, and that's where these wt's came in. So we have those weights wt that tells us how much I listen to the advice of each ht. And the wt's will usually be proportional, inversely proportional to the error. HTs that made small error, I will give them more honor and respect the view, and so I'll give them more weight. And HTs that made a lot of error, I give them small weight. Yes?
How do we determine capital T?
Yeah, so I'm saying, or either we fix it in advance, or in practice, I mean, you have some running time where you want to stop, or you look at the error, you can calculate the error of each of those, and you hope that the error keeps shrinking, and when it stabilizes, you decide, I'm not making any more progress, I'll stop here.
Is there like an optimal point after which you start getting more error? Or
No, so we'll talk about it. We'll talk about what is the cost of running it for too long. So there is a benefit and a cost of running it long. So I keep running my algorithm, I keep chewing over and over and over my sample. Right? So now the big question is, what do we gain or lose by picking large t, by running it for a lot of steps. Okay? Lose is 1s or 1 or 2o?
1.
1. Okay, I'm fine. It sounds like 2, but it's okay. Okay. So that's the next point I want to discuss. Yes.
For our sign of the summation here, I understand that W is like an actual number, but isn't H and T a function or a set?
Okay, so what I mean by sign, I mean that for every point x, h of x will be the sign of ht of x.
Oh, and then the sign is just like looking at all.
The sign is those HTs, those H's. I view them as predicting either +1 or -1. So each HT goes from my domain to +1, -1. So each function in my class gives labels either +1 or -1. Then I take those. I take the sum of weights. So I have a point x. I have to predict a label for x. So I look at which h's said it's plus, which h's said it's minus, and I look at the weights. And by taking the sign, I'm putting on two sides of my scale, all those that say +1, all those that say -1, each of them weighted by WT, and I see which side of my scale wins. And that's the sign that I'll give to x. Yes?
Sorry, it's my point. The I should be a little t.
The I should be little t, right? That's a small correction, right? Yeah, thank you. So that's basically what is the boosting paradigm. And the AdaBoost was a specific rule for picking those updates from t to dt +1 and picking the weights WT at the end. Now so this is a very simple procedure. And we can run it efficiently provided what? What is the subroutine that I keep using it over and over again that may cost me some computation time? The ERM. My subroutine is each time I have to pick an HT that minimizes the error with respect to my new distribution. Everything else is very clearly determined, how I update the distribution. But now I have this, so I have to pick my class B to be such that it's very easy to pick an ERM, a risk minimizer in the class B. Because that's where I'm paying my computation. Any other questions? So do you have a very simple algorithm, runs efficiently if I picked a very simple B. Now I want to discuss the issue of the size of for how long, for how many steps will I run it. And now we have two in general. So what we're going to use, we want to minimize the error of the output, right? So we know that if H comes from some big class H, and VC of H equals D, then we know that for every distribution, for every data distribution P, we know that the error of H with respect to B is bounded by the error of H with respect to a sample. And this is provided the sample is picked IID from P. And we have here plus VC dimension of h plus my ln 1 over delta divided by m and square root. M is the size of S. This is provided S is an IID sample from P. So here I just repeat our fundamental theorem, right? Our fundamental theorem tells me my error consists of two components. One is my empirical error, and one is my generalization error. Now let us consider what is happening when I'm running this boosting and try to apply this bound. So when I'm moving, my h is going to be this h. That's the outcome of my boosting algorithm. Right? So what I want to show is that as t grows, the empirical error of this h goes down. On the other hand, as t grows, which component may grow up? What may increase as I run it? Yes. The Viz dimension of what?
The class here.
You're right. So what is my class? My class here, each time, it's the class of all possible combinations. And as t grows, I have more and more combinations to consider. So as t grows, the class from which h is coming is a bigger class. It's a class of longer combinations. So as t grows, the Viz dimension of this class of combinations grows. So we want to bound how much the error, the empirical error, improves as I'm increasing my repetitions, and how much the Viz dimension grows, and we want to trade them one against the other. So we need two results here. One of them I will just cite, and the other one I will prove, because the proof is kind of simple and very similar to things that we have already done. So what are the two results that I need? I want to show you a bound on the empirical error of h. I mean, I have h, I have this original sample, and I want to check how much error I make on this original sample with this combined h. And I want to show you that it goes down as we add more and more components. And the other part will be to bound the Viz dimension of this set of all possible combinations from which my new h is coming. Okay, so the first result is that bounding ls of h. And the theorem here is that if every ht is or let's put it like this, has error at most half minus gamma on S with respect to dt. So if at each step I manage to give you a gamma weak learner, at every step I was away from a half, my error was away from a half by a factor, by a shift of gamma. So my HT was all through a gamma weak learner. Then I have a bound on the total error. And the bound on the total error, where do I have it? Somewhere hidden in my notes. And I also gave it to you last time, but okay. So then LS of my combination after t steps is at most e to the minus 2 gamma squared t, where h is the result of running AdaBoost for t steps. So we see that if we can be bounded away from a half by gamma, then as I add more and more steps, my error goes down exponentially fast with the number of steps, my empirical error. You see, so this part, this component, goes down exponentially fast as I add more and more HTs. But of course, could be the case that at some point I cannot find any HT that will have error less than 1/2 minus gamma. So I may stop if I see that my next HT doesn't satisfy my condition, then it's not good enough. And we can also replace it. Instead of having here a fixed gamma, I can have a formula with gamma t, which is by how much the HT is away from a half. But basically, you can think of it, we fix some threshold gamma, we keep shrinking our empirical error exponentially fast, and in many cases, we will be able to get to 0 error on the sample, 0 error on the sample. So what is missing now? In order to, did we have a miracle and we can get 0 error on every distribution? What is still missing now? The other term is still missing, right? OK, so now the other term. And for the other term, we need an analysis of the VC dimension. So this was lemma 1. And my second task is bounding the VC dimension of the class H from which the boosting output comes. Right? My output is this function. So let us formalize it by definition. So we have here a small definition. Given any class, a class B of and a number T, let LBT be the class of all possible outcomes that I can arrive at after T steps. So it's the class of all sine of sigma wi hi, I goes from 1 to t, such that wi's are real numbers and the hi's come from B. So this is the class of all potential outputs after T steps. And I want to bound the VC dimension of this class. So I'll see how much do I pay in terms of generalization by increasing the number of iterations of the boosting algorithm. Yes.
Is the class L here same to the class H?
Yeah. That's the class H. This class is the H that we need to refer to when we have the boundary, because it's the class from which my final output is coming. Right. It's a good point. This is going to be my H. So I want to bound the VC dimension of this class. And I want to bound this VC dimension in terms of the VC dimension of a small class B and the number of iterations T. Okay? So we have here a claim, or a theorem if you want, that for every class B of finite VC dim, so say VC dimension of B is some D, and every T, the VC dimension of this class LBT is at most D plus 1 times T times the log of the same thing, D plus 1 times T plus 2, or something like that. So basically, the VC dimension increases. I can check the exact formula. There are some 2s and 3s running around. Yeah, there's maybe a 3 here. But it doesn't really, what matters is the basic idea. I have a 3. Yeah, something like that. Anyway, what is the basic idea? That the VC dimension of this guy is roughly the VC dimension of B times T. That's the main factor. And then I have log of the same thing. So if B has low VC dimension, what I'm paying is each time I do another iteration is I increase my VC dimension by another VC dimension of B. So as I do more and more iterations, I'm increasing this term here. Are we still on the same page? Is it clear where we are? We describe the AdaBoost paradigm, and we want to have a consideration of what do we gain or lose by making more steps. And it seems that, and then we refer to the basic fundamental result, and we said that there are 2 effects to having more steps: the empirical error and the VC dimension, which is generalization. The difference between the empirical error and the true error. The more complex my H, the more risk I run of overfitting. That although it looks nice on the sample, it will be bad in reality. And this overfitting is controlled by the VC dimension. Yes?
So we said that L of B comma T is our H that we're looking through?
Right, because this is my outcome of this procedure is coming from this H. The outcome of the boosting always looks like this.
Okay. And on this side of the board, we wrote the VC dimensionality of H is equal to D. So is that a
No.
different H?
That's a different, the different D. So you will get a point for saving me from confusing you with the board.
Okay.
This was with some intention that here, instead of writing VC dimension, I'll write D. But it's not the D that I care about.
Yeah,
Right. Okay. So he saved me from confusing those that pay attention to the board. But maybe nobody would save it. But okay, this is the VC dimension of the big H, and I'm saving D for the VC dimension of the small basic class B. And the big H is all combinations of classifiers from the basic class. Okay, so now we will have the proof is very short, basically. So we'll just do this proof, then we will discuss boosting in reality. Okay, so the proof is basically, for many cases where we want to bound the VC dimension of a combined class that is composed of other classes, the basic tool that is most useful is the Summerlemma. So what is the Summerlemma? Or the trick is that assume the class L of Bt shatters some set of size m. And we want to show that m cannot be too big. That will be our proof of the bound on the VC dimension, right? In that case, we know that I have to be able to cut from this set all possible behaviors, right? So some set, let us call this set A. In that case, the set of all H intersection A such that H is in my H, in my LBT, should have what size? What should be the size of this set if I'm shattering a set of size M? Yes? What? Right, it should be greater or equal to 2 to the m. It should be just, it cannot be greater. It will be equal to the m, right? Because shattering means I'm getting here all possible subsets. But now I will show you an upper bound on this. And from this upper bound, which will include m, we will get a bound to how big m can be. So what is going to be the upper bound? So I want to upper bound this set. So I'm saying that this set of all H intersection A such that H coming from LBT, I can kind of control it. It's at most what? So every hypothesis here is determined by picking H1 to HT from B and then picking a combination. Right? Now I want to just check behaviors on A. So how many behaviors, I want to bound how many behaviors, what is the size of the set of all H intersection with A such that A comes from B? What can I say about this size? How many behaviors can I get on the set A from the set B? You see, I'm using here H's in B. Not big combinations. And I know that B has VC dimension D, and I want to use a Summerlemma. So what will I get here by the Summerlemma? By the Summerlemma, this is sour. This is at most m to the d. Right? The Summerlemma told us, you remember the Summerlemma said where the number of sets we can cut goes exponentially up to the VC dimension. And once we hit the VC dimension, the number of possible behaviors is a polynomial m to the d, bounded by a polynomial m to the d. Now if I want to pick t of those, so the number of combinations, so the number of t combinations of such subsets is at most m to the d to the power t. You see, what I'm trying to analyze is how many behaviors can I get by this class. But to pick an h from this class, I pick t elements from the original h. So I picked t behaviors from here, and each such behavior was from B. So each such behavior was one of those m to the d possible behaviors. So this is m to the dt. Again, when I want to pick, where is my, you see, I want to pick a function. This is an h. And I want to see in how many ways can I pick such an h. So to pick such an h, I can factor it into two steps. First, I have to pick my hi's. How many ways do I have to pick my hi's? That's what I calculated here. Over a fixed set A, I have to pick t hi's. Each of them can choose among the behaviors of the class B over A. So I have to pick t elements hi. Each of them is one of these behaviors, one of these m to the d behaviors. So I have m to the dt ways of picking the vector of hi's. Now, if the vector is fixed, note that if I fix the hi's, the function that I have here, sine of sigma wi hi, is actually a linear classifier. You remember the linear classifiers. Linear classifiers were always of the form sine of sigma I goes from 1 to some t, wi xi, right? These were half spaces. But now I fixed each hi. Instead of xi, I'm writing here hi of x. I have an input. I calculate hi of x. But that doesn't matter. This is just a fixed number. It's like the coordinates of my x is h1 of x, h2 of x, h3 of x. It's just a different way of representing my x. So what do we know about the VC dimension of this class, of classifiers like this? So the VC dimension of this, what is the VC dimension of linear half spaces of dimension t? You're just doing your assignment, yes. T plus 1, but they are even homogeneous. There is no, so t, it's just t. So once I fixed my hi's, I only have m to the t possible behaviors. So this is bounded by m to the dt possible ways of picking the hi's times m to the t. Once I fixed my hi's, I only have so many behaviors because it's a Vichy domain. Now it looks like a linear class over t coordinates. My t coordinates is h1 of x, h2 of x, up to ht of x. So in total, if I shatter a set M, if we kind of converge this calculation, we get that if I shatter a set M, I have to satisfy the equation, then this, which equals this, should be greater than this. So I get that I have to satisfy the equation that m to the dt times m to the t will be greater or equal to the m. In other words, m to the t plus 1 d should be greater than 2 to the m in order to shatter. Yes? D plus 1 t. Good. That's the point. It's d plus 1 t. So send me your email, and who was the other one with the u? Yeah. Okay. Okay. So you see what is happening now is I'm saying this bounds m. This says m cannot be too big. Because what happens when m grows? This is an exponential function. This is a polynomial function in m. So this guy grows much faster than the other guy. So If I want to shatter a set of size m, I can draw these two functions. So here is m, and here I have the function m to the td, which is some m to the d plus 1 t. And I have the function 2 to the m. And the function 2 to the m grows much faster. So for big enough m, 2 to the m will be bigger than this. But I can also only shatter a sets where 2 to the m is smaller than this. So if I shatter a set of size m, m cannot be too big. If m is too big, then 2 to the m should be above. And now it's just a matter of calculation, simple calculation, to see that if I substitute for m the VC dimension that I promised you here, substitute this for m. This is a shattered set, right? The VC dimension is the size of a shattered set. So I'm trying to shatter a set of this size. If we substitute this m here, we see that it's already past the crossing point. If we substitute this m here, we will see that this one is already smaller than this one. So m cannot be too big, so big. The crossing point, the maximum VC dimension, is smaller than that. So now all that is left is to take my bound, substitute it for m here and here, and see that this guy is already bigger than this guy. That the m that I picked here, this formula here, 3d plus 1 t log d plus 1 t plus 2, something like that. If I substitute this m here, it's already in 2 to the m will be bigger than m to the dt. And therefore, the VC dimension should be below it. So that's a general style of proving bounds on the VC dimension of complex classes based on the Sauer lemma. We use the Sauer lemma here to say that since B has a small VC dimension, B can cut only few behaviors from A. OK, so that is the analysis that we needed to get an estimate of the benefits and risks of running boosting further and further. We run it more, we decrease the error here, but we increase the VC dimension. So that's as far as the theoretical analysis of boosting goes. Are there any questions here? This kind of argument is, I think that I asked it, there was no need to use it in the assignment, in the last assignment? Probably not. In the assignment before, maybe. If not, then it will be in the assignment after.
I have a question.
Yes.
I understand where the m to the dt comes from, and the m to the t, but I don't understand why we multiply them. Or maybe I don't understand.
Oh, no. It's a very good question. Why do we multiply them? Because I'm saying that there are m to the dt possible ways of choosing h1 to ht.
M to the d ways, because we have m things in every sample, and the d is our VC dimensionality. So
Right. It's m to the d ways of choosing each of them. But when you want to choose t of them, you have the exponent of t here. So there are so many ways of choosing h1 to ht. For each of these choices, once it's being chosen, then we need to worry about choosing the w's. And now, once those are fixed, the w's are just defining a linear threshold function over this representation. So for each of these, there are so many ways of defining a linear threshold function.
Okay.
You see, what we did here is we thought of it like that. Once I picked h1 up to ht from B. Now my classifier looks like this. H of x is the sine of the sum of wi, I goes from 1 to t, of h I of x. Right? But now I can look at it, I can view it as following. I took x and I re-represented x as a vector. h1 of x up to ht of x. So I took any x and mapped it into some Euclidean space. This is a member of R to the power t. I took every point x and mapped it as a vector. And now I have a linear classifier over this space. So if I fix the h's, I fix this mapping, and now all my x's become members of this RT, and I'm taking a linear classifier. So once I fix the h's, there are at most so many linear classifiers, linear partitions over m points. So we can really think of it as some way of doing a new representation of my x's. I had some point x, and I fixed my h's. Then I represent every h as a point in RT. I had some space here. That was my sample, x1 to xm. And I map it into some big Euclidean space. Every point is mapped to the vector h1 of x up to ht of x. So every point now of x is represented by a point in this real vector space. And I'm picking my classifier as a linear classifier over this space.
And since
and now, if I have m points in this space, I have at most m to the t many linear partitions. Because the VC dimension of linear classifiers over T is just t.
so there's T linear classifiers, and then why?
No, not T-linear classifiers. I'm looking at all possible. I represented every point as a point in RT.
Right.
This is my space RT. So now I have m points in RT.
Right.
And now the sine, this guy, is a linear classifier over this representation.
Okay.
So I ask, how many ways do I have to cut by a line m points in RT? And I'm using Summerlemma again. We know that the VC dimension of homogeneous linear spaces in dimension t is just t. And therefore, by the Summerlemma, if I have m points, I have at most m to the t ways of partitioning them with members of this class H. So this is Summerlemma again. So these are as many, how many ways do I have to choose the H1 to HT? Then I use Summerlemma again, because after I chose the H's, it's a linear classifier. And for each of them, there are at most so many partitions. So we have at least one student to make an effort to follow. And I really appreciate it. But if there are other of you that want to make the effort to ask more questions. So we can think of the boosting algorithm. Each time I do another iteration, I generate another HT. And now I'm representing my points as a longer vector. And then taking linear classifier over those representations. And we will see later that this idea of taking some sample and embedding it in some high-dimensional Euclidean space and taking a linear classifier over this Euclidean space is a very common idea in other algorithms in machine learning as well. Yes?
So you say that you project each of the xi to xm into RT, but isn't x something that's in like not RT?
Yeah, x is, I don't know where x is coming from. You see, think of it like this. Here I have patients. And each HI is some measurement of the patient. So H1 of my patient could be its age. And H2 of my patient could be its temperature. And H3 of my patient could be its blood pressure. And each time I do a different iteration, I come up with a different classifier, and this different classifier gives a number to every point x. So now every patient is represented as this vector of measurements. So those were patients. I don't care in which space they lived. But now each of them is represented by a vector of measurements. Each HI measures something from x. And I combine those measurements. Okay? So now let us show how this is something which is really useful in practice. So what I want to describe to you is a really practical algorithm that uses this for face recognition. Yes?
I was going to ask, so this space is actually like minus 1, 1 to the power of d. If your HIs are...
No, but the HIs, if the HIs are minus 1 plus 1, it's minus 1, 1 to the power d. So it's even more restricted. I mean, I can look at minus 1. That's a good point. It's minus 1, 1 to the d. So for each patient, it's not just age, it's just old, young. Fever, no fever. High blood pressure, not high blood pressure. But those points plus 1, minus 1 are in particular points in RD. Yeah, it's a good point. Any more questions? OK, so let me show you some nice practical application of this. And this is work on face detection. So face detection is a kind of a classical challenge in image analysis. I give you an image, and I ask you to find the faces there. And we know that nowadays, every camera does it automatically. You know, you look at your camera, it gives you small squares around the faces. Or you will go to the Facebook image, it gives you small squares about the faces to label them with names. But it used to be a very difficult task, how to detect faces. And there are all kinds of known examples where they apply it in a soccer field, and it takes the ball and thinks it's a face because it has those black and white hexagons. And anyway. So this was a big challenge until about 15 years ago, 20 years ago. And it was solved with this, kind of solved technically, satisfactorily with this method. So it's a face detection algorithm. This is by Viola, which is a professor at MIT, and someone that I don't remember his name, based on boosting, on exactly the same method that we learned now. So your input is an image. So let us assume that your inputs are images, and say they are black and white, grayscale, with, say, 24 by 24 pixels. So every image is such a 24 by 24 pixels. Each pixel is some level of gray. And you want to detect faces. So now we are going to define what is our basic class B. So we want to do boosting. So we want to choose a basic class B that we can easily do ERM over. So what is the class B? The class of basic classifiers B, or basic functions B, is going to be as follows. So we are going to consider every class H, every H in B is determined by a rectangle in the image and one of 4 types: A, B, C, D. So here is my image, and I look at all possible rectangles. So I look at all possible rectangles. And for every rectangle, I will have 4 classifiers. And the 4 classifiers that are associated with a given rectangle are determined by, the first thing is you look at your rectangle, and you divide the rectangle like this, and like half like this, and you sum up the levels of gray here, and look at the difference between this and the levels of gray here. So it's the difference between the average level of gray in the top half of the rectangle and the average level of gray in the bottom half of the rectangle. And well, I think it's, anyway, I may be adding some. So we have this guy that compares the left and the right. We have a guy like this that divides the picture into 3 and compares the gray level in the center to the gray level on the sides. And we have a similar guy. And we have this guy, and we have a guy like this that compares the average gray level in these 2 boxes to the average gray level in these 2 boxes. So we have some basic types. So every classifier picks a rectangle. Every classifier in my class picks a rectangle. And in this rectangle, it picks what am I going to focus on: top versus bottom, right versus left, center versus sides, or this diagonal. And when you focus on one of those, you just take the average gray level in one part of the picture and compare it to the average gray level in the other part of the picture, and you get a number in the interval 0, 1. By how much there is a difference in brightness between these 2 areas. So how many classifiers do I have here? Or how many, not classifiers, but how many types of classifiers do I have? How many classifiers do we have here? So we have to pick a rectangle. If the picture is 24 by 24 pixels, so to pick a rectangle, I have to pick 2 points to be the left and right most corners, and 2 points to be the top and bottom. So I have 24 ways to the power 4 options of picking a rectangle, times 4 to pick a type. So I have so many classifiers. And now I just do decision stamps over this. So I take an image. Now it's again the same trick. I take an image. So you have here an image, some picture. And you map it into a vector. And the vector is of size 24 to the 4 times 4. And the vector is the scores that you get on every rectangle and every comparison. So we took every image and we embedded it in Rn as a vector of scores. Make sense so far? You see, it's the same idea. We take some instances that we want to classify, we embed them into some high-dimensional space. Every image now gets this huge vector of scores. Now, the classifiers that I am going to use here is the Sine stamps. The Sine stamps in this very big dimension. In this dimension, 24 to the 4 times 4. This is going to be my class B. And we saw last time that if I give you a training sample, so what is happening now? I give you a training sample. I want to show you that we can learn this class, we can do ERM over this class efficiently. So this is my class B. My class B is the decision stamps. Now, let us recall what is the class of decision stamps. You get data, which is, I cannot draw on the board this dimension. So I'll settle for dimension 2, just to get the idea. Yes?
Quick question. So we said that each element of B is a rectangle that's one of 4 types.
Right.
So there's 24 to the 4 ways to pick a rectangle and 4 types.
Right.
So isn't that B? How is like our decision steps?
Oh, I'll define what it is. I'll describe now what the decision step. But the only thing that I want you to understand so far is that I took an image and made it into a vector of real numbers of that length. Now, assume that the dimension that I drew here, this big dimension. So now you get a training sample. So a training sample, you get image 1, and it tells you it is a face. And you get image 2, and it tells you it's not a face. And you get image 3, and it tells you it's not a face, and this one is a face, and not a face, is a face, and so on. So this is your training data. What does it mean to get an ERM decision stamp? So what I try to do, you remember the decision stamps were very simple classifiers. I just took a threshold in one dimension and said, what will happen if I predict all of this is plus and all of this is minus? How many errors will I make? And I check it for every possible threshold to pick, and I check it on every dimension. And I want to find which one will give me the minimum error. You see, so I have training data, which is images, classified face, no face. I embed them in this high dimension. So now I get a collection of m points in high dimension. Each of them is classified plus or minus, face or no face. Now I'm searching for an ERM over this class B. What does it mean to search for an ERM of this class B? I pick a dimension, and I want to find the classifier along the dimension that will make just this projection along this dimension, such that if I mark all of those as plus and all of those as minus, or the other way around, I'll get as minimum error as possible. And I want to minimize it over the sample for all possible dimension and all possible cutting points, threshold points. And we saw that we can do this in time ERM over this class B of a sample S can be done in time roughly O of MD. You remember, that's what part of our discussion last time. You're laughing because there's the D again? Or what?
Because you said roughly, and then you drew a tilde last time, and I remember how it was easy.
OK, so that's here. Anyway, so we can do it in time. You see, so the running time, this number is not so outrageous for running time. This is my dimension. right? And I multiply it by the sample size. So I can really carry out this ERM, and I can carry out even if I give you weights to the points. Having weights on the points, as the boosting algorithm requires, doesn't make it more difficult to compute. You just pick your threshold, mark all of those as plus, all of those as minus, see where you made errors, and add up the weights of all your errors. That's all. So this can be implemented very nicely. And then we do boosting. And it turns out that this really works well. So let me just try to convince you why it works well. Because this kind of choice of representation really depends on our prior knowledge on how images of face look like. So if you run it on a real, all I did here is just convince you that we can apply boosting. In terms of computational time, it will not be too much. Yes?
So each step of the ERM
each step of the ERM just
just goes for all the
gives a weighting to these points and try to say, with respect to this weighting, what will be our choice now? See, so it could be that initially I had, say just a very simple example. So say that I had these points, plus, plus, minus, plus, right? So initially, if I wanted to, what can we do to make it more interesting? Say I have a minus here. Initially, my best prediction was this guy. And then this guy, which is minus here and plus here, made an error here. Now I suddenly make this point more important. Now it's very important to you not to err here. So maybe your next prediction will be something here. And this will be a minus, and this will be a plus. This will be your H2. And then you reweigh them again and find H3. And each H can go, each HI can go along a different coordinate and pick a different threshold. Just you want to minimize the weighted error each time. And then you take the combination. But why does it fit faces so nicely? Because if you have a face, I mean, I'm very bad at drawing, but let's try to draw a face. Right? So it seems that if we look at the question is, which of those classifiers over which rectangle will give me the biggest contrast to start with? And usually in the face, we get a very big contrast, say, if we take this rectangle here, and this is dark, and this is bright. If I look at an image of your face, because the light is reflected from your nose, but in your eyes, they are more sunk. So this could often be the first classifier. So it's a classifier of this type, and the rectangle is sitting around the eyes. Another good classifiers could be the classifier that sits here. So here is your face. This is your nose. Usually there is a very good classifier sitting here, again, doing this partition, up and down. Because, again, the eyes are dark, the cheeks are bright. You get a big contrast between the bottom half and the top half of your rectangle. So each time you run what is the best classifier of this type, the best rectangle over the image, and you enhance your classifier and do your weighting. Now, what kind of prior assumptions, how can you make this, if this is my algorithm, how can you make it fail, for example? Yes?
Are the rectangles axis aligned?
The rectangles are axis aligned.
Oh, so
Right. So if we tilt the face, this may fail. Because this was based on the assumption that my face is straightforward, and therefore I see this contrast between up and down. If I tilt the image, it may disrupt it very badly. And the problem is that if I allow here all rotations, I will increase my feature space by a lot, and everything will run more slowly. So this is a good classifier for straightforward face that fill up the picture. So I give you a picture which is either a face which is straight up all over the image, or something which is not a face, and you want to decide whether it's a face or not, this will be a very good job. But you see, it's based on some prior knowledge of how faces look and how they are arranged in my image. And you can kill it by playing with it. And the same way, we have very good images for character recognition. And how do we kill them? The CAPTCHA, for example, kills those character recognition. You know what? When you have to fill in your, right? So the character recognition, you just figure out what it is based on, say detecting straight lines, and then you take your letters 4, 3, 2, 5, and add all kind of these guys. And the character recognition that was based on small features that wanted to detect lines get completely confused. Then they realize that this is what you're doing with your CAPTCHA, so they build new features to find this, and then you say, OK, my next CAPTCHA will look like this, and will confuse the new classifier. So there is a game here between, I mean, that's the no free lunch. We cannot have a classifier that will solve all the problems. But if we know what our problem is, we can design features that fit the problem and get a very nice performance with boosting. Yes?
Is there any reason why it's 24 to the power of 4 instead of just 24 to the power of 2?
Well, you have to pick the left and right ends of your rectangle and the top and bottom.
So the rectangle is uniquely defined by like these 2 points.
Ah, you see, I just need these 2 points. But each of these 2 points have 2 dimensions.
Oh.
So it's the same thing. OK? OK, so have a nice weekend, and we'll continue next week.